So what does that mean? Well, we just have two bar elements. We're going to have displacement at the first node, second node, and third node. Well, boundary conditions, as we were talking with Elias earlier, right? We have either the force or displacement, so we can prescribe say R sub I or D sub I, but not both. That's why when we solve our system of equations and we have a force that's applied directly to a node that's pinned, right? The forces that we determine from our equations, right? The inverse, or KD equals F, right? Once we know our global displacements, we don't get to see that R sub I. We don't get to see that force that's applied directly to a node that's pinned because we impose the boundary conditions that it's pinned in the first place. So you're never going to calculate that. So we need to make sure we take that into consideration. So in this case, if what Cook does is he assumes that we know R1, R2, and D2. So we have three boundary conditions. We know the forces that are applied at nodes 1 and 2. And then we have a known displacement, right? D2.
Those are forces, not
reactions forces, yep. And if that's the case, right, knowing that we prescribe one and not the other, that means D1, D2, and R2 are unknown.
Yeah, something right.
What was that? Oh, 3, sorry. Thank you, Amanda, for being so nice about that.
Not nice to say something weird.
That's fucked up.
Dumbass.
Yeah. Does that work? No, that doesn't work. What are you doing? R3. This is R3.
I remember the first time I tried to write something.
I know. Woo!
Be a better handwriting, but you write the wrong thing.
Yeah. So what's better? So what do we do? Well, we can rearrange our stiffness matrices, essentially pulling out anything that is attached to D2, because D2 is known, and we're going to take all of our stiffness values associated, right? This is our force vector associated with the displacement at 2. We're going to pull it over to our forces, right? Because K12, K22, and K32 times D2 are essentially our forces at 1, 2, and 3. Hopefully you're comfortable there, Mike.
I'm doing good.
So we're going to pulling out all, right, displacement 2 products to the right side. Here we go again. We're going to do this big matrix. Now we have R1 minus K12 delta 2, R2 minus K22 delta 2, and then R3 minus K32 delta 2. Again, we have our displacements D1, D2, and D3. K11, K12, oops, sorry, 2-1. K31, these now become 0. So we essentially took our load vector, we pull it out, right, because it's known. We know our displacement, that delta 2, so we can pull it out. Well, we have, unfortunately, some problems with this. One is that there's no symmetry, so that this will end up being singular if we take the inverse of this matrix, which we're gonna wanna do, right, to calculate our displacements, and then using those displacements, we can calculate our forces. And then also this quantity of R2 minus K22 delta 2 has knowns and unknowns, right? Because R2 is unknown, but delta 2 is known.
Delta 2 is the same thing as D2.
Yes. Yeah, that's our known displacement. So we said delta D2 is known, and it's known as delta 2, the displacement at 2. So now we have no symmetry. And R2 minus K22 delta 2 contains knowns and unknowns. All right, the knowns being delta 2, the unknowns being R2. And we really want, right, displacements equal to the inverse of our stiffness matrix times the force vector. So how do we fix that? Well, we say, all right, our second equation can be replaced with just our known quantity, right? We could say that D2 equals delta 2. So this second row in our stiffness matrices essentially will be replaced by zeros with unity at our location that gets multiplied by D2, right? So essentially our new equation becomes K11, 0, K13, 0, unity, 0, K31, 0, K33, times D1, D2, D3. Again, now we have our R1, K12, delta 2, delta 2, and R3 minus K32, delta 2, right? Well, now we have a matrix that can be inverted to calculate our displacements. This is if we knew the displacement at 2 was delta 2. If our displacement was 0, right, all of those would go to 0. And it would be very simple, right? So if we have a pin connection, some sort of fixity that destroys the ability for this thing to move, right? That delta 2 now is known as 0, and it simplifies that equation. So our force vector becomes more simple, or simpler. Sometimes adding all of these zeros and going through this method takes a lot of memory, right, on the computer side. Simpler than partitioning and multiplying out all these equations, solving for all the unknowns, plugging back in, right? So now we're still manipulating the K matrix, so we can just take the inverse, multiply it by our force vector. And so what we can do is sometimes instead of just even zeroing out these rows and columns, right, that are associated with our known displacement or boundary condition, we could just omit our suppressed degrees of freedom or degrees of freedoms, as long as our displacements were 0. If 0, well then that big stiffness matrix up above is just K11, right? K13, K31, and K33. And we didn't even have to build this 3x3 matrix. That 3x3 now becomes a 2x2. We know, right, from the beginning what these externally applied forces are, reactions are R1 and R3. We have a stiffness matrix that can be inverted. We can calculate our displacements at 1 and 3, right? Then going back and taking those displacements, we would put it back into the original big unmanipulated, right, 3x3 stiffness matrix. We would multiply this out and we would get our final forces, right? Our R2 is really what we would be missing. Or, as I mentioned on Friday, there's a method with which we would essentially create a spring of infinite stiffness, which makes sense, right? If we were imposing zero displacements, well, that support essentially has infinite stiffness. It's not allowing it to move. So if it doesn't allow it to move, we end up with this matrix where we would essentially just replace our stiffness associated with D2 as infinite. We would solve, right? Solving this, again, is only going to give you the displacements, right, that are outside of the boundary conditions. And then we would go back through, the displacements outside the boundary conditions. Then we'd go back and then you would calculate your overall forces. Okay. Personally, I like that method where it goes zeros and ones, but a little harder to program.
Column associated with D2, like the
Yeah, but it's
K1, K2, K2, K1, 2.
But it's associated with known forces where you're originally calculating unknown displacements. And so you really want the rows associated and really the stiffness associated with your displacements, right? So you're calculating the inverse.
So do you
That's
not
the one you're
make-
manipulating.
Do you not make D2 equal to 0? Or like you don't put in that known displacement of
No,
D2? You don't.
no, because you're taking the inverse of k times the force vector so that you can calculate the displacements.
And then D2 will come out as 0.
And then D2 will come out as 0.
Is it right to have R2 0?
Yes.
Isn't that your reaction?
Yeah, but it's
Or we
unknown.
don't know.
And so when you take the inverse of this, that doesn't end up playing any role in it, right? Because then it gives you the displacements, which pumps out this as 0. And then you pump this back into the original one that's unmanipulated, and then you're going to get a value.
Yeah. So you're
You could put anything there.
That's right.
You could
Okay.
put anything
Put
there.
anything right there. Okay, yeah. Okay.
You could put anything there.
Thank you.
All right, any questions? I posted the homework, which I'm sure all of you are as studious as Daniel. And already looked at it, and we're getting out MATLAB, and we're stoked about it, even though I posted it at like 7:30 this morning. Okay. Came in here bright and early, asking me bunches of questions about it.
What a nerd. Daniel.
All right.
You're excited, man. Me too. I like this stuff.
Due next Wednesday, okay? Because obviously Mondays are hard for you guys, apparently. And I'm a pushover, and then maybe there's Super Bowls on Sunday, so I was also told you wouldn't be doing homework anyway, for those of you watching the Super Bowl. Essentially, I'm asking you to devise a MATLAB function that determines, based on geometric parameters of our truss, right, and the applied.
Tim, you'll be here to pick it up on Monday, is that correct?
We don't need to talk about that, Mike. We don't need to talk about that, Mike.
All right.
I'll be gone all next week. I think I mentioned that to you. But we'll be
Yeah, where are
doing
you- Where are you
online.
going? What's the-
It's a work-related thing. Work-related thing. It kind of is. It's for the in-laws.
Yeah, that's right.
So I mean, I had no choice in the
Yeah,
matter.
yeah.
Okay. So essentially, Mike's going to talk about it. Hopefully today he'll get to functions. He's got to eat up our time, but essentially 4 functions, which are really just scripts or sections of code that allow you to input in MATLAB known values, right, variables, and it will give you out predetermined outputs, right? In this case, I want you to put in what's the applied load, the material properties, area, cross-sectional area, and the geometric setup of this truss, right? And it's going to pump out to you the global reactions or forces and the global displacements, right, in vector form. And then you will subsequently use that as you move down through parts 2, 3, and 4, writing additional functions that allow you to plot the displacements, right? So essentially, I want to see the undisplaced and displaced shape of this truss. I want you to calculate what the axial forces in each of the members are. And then I also want you to plot the displacements in element 1, right, as we go along the way. Okay? We'll want you to add comments to your code, which Mike will go over how you do that, okay, if you're not familiar with that. I've outlined these required functions, but sometimes it might make sense to write additional functions to make things easier. Maybe it will help you, maybe it won't, okay, that's up to you guys. Part A, right, when we talk about solving our global displacements and forces, I expect that the solution process in your function will follow our solution process that we outlined, right? Where we start at the local side, we do local stiffness, we transform, we develop our global stiffness, right? We have to impose boundary conditions, we gotta go through all of our steps, right? And then finally, I'll set up a drop or like a box in D2L so you guys can drop your actual code, because I'm gonna go through and have my own numbers and my own code. And I'm gonna, I could, essentially when you're done with this, you're gonna have 4 functions, and I should be able to evaluate these functions at any values of P, E, A, B, and H, right? And it should match my code, okay? So that's the end. That's the end game.
That's an actual thing we need to write, like the function signature, solve, trust.
Yeah, so when you go, this is what
Like that literally.
this is the syntax for establishing the function in MATLAB. When you do it in MATLAB, you essentially take off this front part and you say, I want to solve truss. So essentially, I want to run this program. Is really what
Solve trust is like a.
is a program. It's a function,
You're
which is
gonna
a
make it.
program. You're going to make that function solve truss to where you put in these inputs, it's going to give these outputs. And then when you go into a script, as long as that script file is in the same folder as all of your function is essentially going to be its own file. It's a .m file. It'll say solve truss.m or something, right? So then I'd be able to open this up, open a script that has your functions in it, and I can say, all right, I want to solve truss and I want to put in these inputs, and it should pump me out the D and F. Does that help you out, Elias? Okay. Yeah, Daniel.
You need to put in one, if you put down all the functions down, I can just put in one MATLAB file that I don't have to separate all 4.
No, you don't have to have 4.m function files,
Yeah,
is that what you're saying? Yes, you can do,
all the way down because they were wet too.
yes, as long as they're embedded into the folder, then I can open a script and it'll call on any one of your functions. Yes, you can do that. Okay.